So welcome everybody to the lecture in dynamic optimization and machine learning. What I would like to do, or what we would like to do today, is first of all we would like to go through the to one of the exercises that we kind of started on Tuesday, and then I will be super briefly tell you something about the infinite horizon case. This is just one slide, and then we move on to the exercises. And I think the exercise that we are discussing now with the finite horizon case nicely leads basically to the infinite horizon case, because there's one thing that actually puzzled me a lot yesterday, and it made me again think that that when solving those things, the most important step is to have a clear notion of what the problem is, so of how to write down the Bellman equation. So once you have that, the rest is fairly simple, really super simple. I mean, it's, you know, when you think about problems, there are two dimensions, right? Either they are complex, or the solution is complex, or a lot of work. Okay. The setting up the Bellman equation was kind of complex. I mean, not really, but you have to think about that a little bit. Finding the solution is just work, and as I told you, work is relatively. I mean, the advantages, you could delegate work, right? The conceptual thing is not that easy to delegate. So that is basically the good news. Okay, let's jump right in. And so can you see my screen?
Yes.
Yes.
Okay, thank you. So what we had is we were confronted basically with a very simple Mickey Mouse problem, where it stated that you were given some objective function. Okay, and the objective function looked like basically the expression here in the brackets. The only exception is that what you have in the slides states that the starting period, so the period in which you start thinking about the problem, which I labeled here tau, is just equal to 1. So if you put tau equal to 1, you are back into everything what we had before. This is basically what you want to maximize by choosing this UT thing. So you want to have a sequence of all the UTs that you want to pick. So all UTs from 1 to capital T minus 1 are the things that you want to determine. Okay, and what you know is that the state, which is labeled by X, is just a function of the previous state, and it's a function of the control, and it's a function of some realization of a shock. Okay, so what you could do, you could rewrite this, and then you would see that the growth rate of the state is a function of your control, so of what you pick, times some shock. Okay, so essentially what you could do is you could rewrite this saying the growth rate of X is the same as a function of the control plus some shock. Right. This is not directly obvious here, but this is basically the main intuition. And what you know is that the stochastic structure that is associated with this shock is super simple. You have only two realizations that this epsilon can be. Either it's 0 or it's 8, and one happens with probability 50%, and the other happens with probability 50%. And the first task was that we should specify the Bellman equation for capital T minus 1 and for capital T. This was the first part of the exercise, and the second part of the exercise was given that you know the general solution for the Bellman equation, for the functional form of the Bellman equation, you should rewrite, or you should derive a relation for the optimal control, and with that in mind, the rest of the exercise was just putting this into the computer. Okay. The thing that puzzled me at first glance is the following. You can see here that every contemporaneous value, if you want to put it that way, is multiplied by 1/2 to the power of t. So you might have the intuition, and this also was my first intuition. Well, this is kind of discounting, right? So this is a discount factor, and what you would like to do in the Bellman equation, we talked about that, is you just look at the contemporaneous value plus the discounted value of the value function. So there was some, at least deep in myself, this intuition that I could get rid of this 1/2 somewhat, and but this is not true, and this is not easily done here in this finite horizon case. And on the next slide you see why this is the case. So let us first of all think, before we come to calculating anything, how would we like to rewrite the recursive structure of this problem? Because only with the recursive structure at hand, we could write down the Bellman equation. So recursive structure means that I can split up the entire problem, so everything that is on this right-hand side, into two expressions. One that tells me something about the contemporaneous thing, and the other about the rest. How can you do that? Well, that's at first glance, that's relatively easy. You could rewrite everything that's here in this bracket. So this is your objective function, right? You could write it bit by bit. So instead of writing this compactly as a sum, you could also write just all the capital T plus 1, or all the capital T parts of the sum, right? So instead of the sum, you could write 1/2 to the power of tau times this square root plus 1/2 to the power of tau plus 1 times this square root. Oh, there's a typo, sorry. That must be tau plus 1, and there must be tau plus 1 as well. I'll correct that. And then you go on and on and on. This looks all the same up to period tau, up to period t, capital T minus 1, okay? And then you have plus, I cannot see that really good. And then you have basically what you get in the last period of your planning horizon. So this is basically this is just rewritten this thing in a less compact way. Okay, so this is what you can do. But then what you can say is you can split this up and write this down as the contemporaneous payoff or the contemporaneous objective plus the rest. So you wanna put this rest together. Okay, and what is then the rest? Well, we could claim that the rest is just the objective function that starts in tau plus 1. Okay, so we could rewrite this saying, okay, look, this is just the contemporaneous value, 1/2 to the power of tau times the square root plus the objective function that starts in the next part of the planning horizon, because this is just the rest of this sum, right? Okay, and why is that? Well, if we go back just one slide, well, then you could see that, right? If you just go back to tau plus 1, well then you have just the rest of the sum that you want to consider. Okay, so now having this said, we have at least a structural idea, I would say, about how the Bellman equation looks like, because this is basically the recursive formulation just of the objective function. But what does the Bellman equation do? Well, the Bellman equation is just the objective function evaluated at the optimal path. So we assume that we follow the optimal path, okay, and write it and then basically substitute or do not consider the expected utility, which is true for anything, for any path that you choose, but we look at the optimal path that you choose. But the recursive structure just remains the same, right? The only thing that you do is that you say, well, this utility that you have at the beginning of your planning horizon, once you follow the optimal path, is just abbreviated and labeled as the v of x tau. So this is the value that you have in tau if you have a state that is labeled x tau. And this is just by definition, or this can be written by this recursive structure definition just as the expected value of this first sum plus the second part of your objective, once again that you follow the optimal path from there on. Okay, so since you only focus on optimal paths, you do not have to consider any objective, but you only have to consider the optimal objective, which you by definition abbreviate by the value function. So this is your v. Okay, so basically what you do is, you can see the value function at the top of the page, because I have,
yes,
I have some the task thing is just hiding that. So I hope there's no typo in there. So basically what you do is you just say, okay, look, if I call the utility function, if I call the utility that I get from pursuing some optimal path by the v, like an indirect objective function, well, then you can write, this is just the Bellman equation. So this is the definition of this left-hand side once you follow the optimal path, which is then equal, obviously, to the optimal u, so the optimal control that you pick contemporaneously, that maximizes the contemporaneous utility. What is the contemporaneous utility? Well, this is just this expression. Once you follow the optimal control, plus from there on you again follow the optimal path, but then you can substitute this, just the regular objective, again by the value function. So this is then the v of x, the v of x tau plus 1. And so the thing is, when you have this, you can just basically split up the problem into just choosing one control, namely the contemporaneous control. So basically what you assume is, you assume the following. You say, okay, look, suppose you follow the optimal path always. What is then your choice concerning, or what is the condition that must be true for your choice of your control today? Given that when you wake up tomorrow, you again follow the optimal path. So by definition, you just focus on a subset of the problem, right? Because you just say, okay, from tomorrow on, I will follow the optimal path, and I do not care how that would look like. The only thing I care about is, what is the optimal choice of my control today, given that from tomorrow on I'm following again the optimal path. This is expressed by this v. So this is, I think, that this is the most important step in solving this exercise, I guess, because once you can write down this structure, well, the rest is just calculations. It's not difficult. Okay, this is just calculation. Once you are here, the rest is really not that difficult. So what I would like you to take into account, what I would like you to suggest is that if you are confronted with any of those problems, it totally makes sense to spend a fair amount of time to finding the optimal Bellman equation formulation. And just a quick note on this discounting thing. And Mark, we talked about that yesterday, right? So if you look at this objective function, okay, you could think that you could extract the 1/2 to the power of tau and put this just out of this sum. What you could do, right? Then you would have just the square root plus 1/2 to the power of 1 of the square root, and so on, blah blah blah. You subtract everywhere the 1/2 to the power of tau. And the thing is, in the infinite horizon case, this flies, because then the rest could be written as the initial problem. In this case, this is not true. You cannot do that. So you cannot just neatly, what I thought, just write the 1/2 in front of the Bellman equation or something, and have the same problem. That doesn't work here, because because the initial problem, so the entirety of this sum, you want to have a recursive formulation for that. But you cannot write down a recursive formulation for that without directly considering this 1/2 to the power of tau, because you could rewrite this as a subproblem, and you could find a recursive formulation for the subproblem, but this is of no help. Okay, so this is an important step. So I think it's very important, just to go step by step. Don't do any guessing work or something. You need to have some recursive structure, or you need to write down explicitly the recursive structure somehow. Okay. And do you have questions so far? Okay, once you have that, well, then it's comparably easy to write down, obviously, the value function for every planning horizon, right? Because we have the value function for a planning period starting at tau. That could be 1, that could be 2, that could be anything. Now we have the capital T minus 1. Well, then you just substitute the tau for the capital T minus 1, and you are there, right? So that's it. This is very easy. And the last period's value function is obviously cannot be written as a recursive problem, because there the time ends. Recursivity, is that a word, recursivity? So the recursiveness of this thing requires, obviously, that it goes on, right? Because you have this today and the rest of the planning horizon. But if you're in the end of your planning horizon, there's nothing else left. So the value function in capital T is just 1/2 to the power of t times the square root. So in capital T, and this is I would say the neat thing in basically all of those, or more, maybe all of those finite horizon problems, there is basically nothing to choose, right? We know what's going on. This is just a description. This just tells you how you feel in the last period. You cannot do contemporaneously. You cannot do anything about that, right? So this is like learning for the exam, right? Just sitting in the exam, things are as they are. You cannot change anything. I can describe, or you can describe how you feel. That's okay, but you cannot do anything, because this is everything that is controllable is over. Okay. Where can we do anything? Well, we can do something in T minus 1, because we can choose the control, which is labeled here as the U capital T minus 1. And what we have is we have a direct effect that affects the contemporaneous utility, or the contemporaneous payoff. And we have a dynamic effect, namely via the expected value function as of tomorrow. And why is that? Well, the reason is, hold on, just focus on this expression. The reason is that with my choice today, I can affect my situation tomorrow. So this is the direct dynamic idea, right? So this dynamic effect, this lies at the heart of any dynamic choice. So if your contemporaneous choice has no spillover into the future, or into further rounds, or whatever you might call this time index, well, then there's no dynamic programming needed, right? So what we want to do is, when we look at this, when we choose this, then we have to take into account this direct effect. Okay, that's easy to find, right? And we have to say something about this indirect effect. Okay, and this is in general the problem. Okay, because we do not know the value, the form of the value function. Okay, but again, now we are starting basically with the recipe, with the cookbook recipe, with the algorithm. Okay, so when we choose the u capital T minus 1, I have to take care of the direct effect. Okay, I know that. This is easy. And I have to take care about the dynamic effect. So I have to say something about what is the expected value of the value function given that I have that I experience x capital T. Okay, because this is what I will effect with my choice. So if I know that, well, then it's easy to know what my future effect will be, right? So do we know that? Well, if we didn't, then we were screwed, obviously, because then we cannot do anything about that. But luckily for us, we know that because we know every part. So let's go through that. Do we know the x capital T? Do we know the value function? And do we know the stochastic structure to calculate this expected value? And all three boxes can be ticked. Okay, and I just go with you through that. So first of all, we know the form of the value function. So we could plug this in, and we have 1/2 capital T square root 2 x capital T. So we know the form of the value function. Check. Do we know how this xt looks like? Yeah, we know that. Okay, because this is given in the exercise. So we can just plug this in. So we could write basically the value function of the x capital T. Check. So the last thing we need to know is, because this is a random variable because the shock occurs here, the last thing we need to know is we need to calculate the expected value of this greenish expression. Can we do that? Yes, we can, because it's very simple. We have just two states. So the epsilon capital T can be either 0 or can be either 8. And we just calculate the expected value of this. Right? This is super easy in a sense. Okay, so this is relatively easy. So once we have that, we can explicitly write down what the expected value of xt is. And we can calculate it. And this is the reddish thing. Okay, this is just the thing that we have in red. And having this, we can use the Bellman equation. So I have to correct myself. The right-hand side of the Bellman equation to write down the first order condition. Okay, because we know. Let's look again at the Bellman equation. So just look at the right-hand side. So at this, you want to know what the optimal u capital T minus 1 is. How to do that? Well, just find the maximum of these two sums, right? One thing, if everything is continuous and nice, one thing to go ahead is just to take the first derivative and set the first derivative to 0. And in the general case, we talked about that. We know the contemporaneous effect. This is known. And we have to take into account the dynamic effect. But to know how the dynamic effect looks like, we need to know the expected value function at x capital T. But we calculated that just. This is what we just calculated. This is the reddish expression. Okay, but then we are there, right? We can just plug this in and take the first derivative. It's just taking the first derivative of a square root equation, which is not too difficult. Okay, and then you can so I take the first derivative of this, plug this in, and then what I can do, I can directly derive an expression that is just a function of the ut minus 1. So this is what I want to do as a function of the state that I'm in. which is x capital T minus 1. This is for me in capital T minus 1, this is not an unknown. I know that. I know the state that I'm in. Okay, I know where I'm today. And this equation tells me, given that today I'm in x capital T minus 1, the best thing to do is to pick the ut minus 1 that just fulfills this equation. Okay. And since this is relatively, I mean, this is designed to be nicely calculated. You see that many things just can be eliminated on both sides. So the 1/2 to the power of capital T can be eliminated. The 1/2 can be eliminated. The 2 times 1/2 is just 1, so we do not care. On both sides, we have this square root thing. You can get rid of the square root, and you have a linear effect or the same effect of the state on both sides. So you can just calculate the u capital T minus 1, which is just 1/2. Okay, this is just 1/2. Okay, knowing that, right? So we know in the last but one period, the best thing to do would be to pick my control to be 1/2. Now I can use this and plug this into the Bellman equation. Okay, so I can substitute the u capital T minus 1 by 1/2. And I can plug in the v of xt. I know how that looks like. This is this. I plug in the u capital T minus 1 and calculate again the expected value. Okay, this is what I've done here. So I just took what we had before and plugged everything in. So we know I plugged in the optimum and used the expectation operator. And what we then have is we just have that the value function in capital T minus 1 is just 1/2 to the power of capital T minus 1 times the square root of 2 times x capital T minus 1. So basically, this looks, when behaving optimally, super similar to what I have in the last period. Okay, very, very, very similar. So now you would state, but hold on, we just have one control, but we need to have all the rest as well. Yeah, that's true. Okay, but knowing this, we can just go back one side. So instead of looking now at the situation or at the optimal control in capital T minus 1, I can look at the optimal control in capital T minus 2 by knowing the optimal value, or by knowing the value function in capital T minus 1. This is what I have, right? I know that. No worries. I know what to do from tomorrow on. Okay, and then I can plug this in. This looks again very, very similar to what we had before. We know again what the x capital T minus 1 is. We know the stochastic structure. We know the value function. So basically, we know everything on the right-hand side. Once we know everything on the right-hand side, we can again take the first derivative with respect to the control, calculate the optimal control, have the optimal control for the next period, and then go on the next period. And what you do is you do basically every time the same. Okay, every step is completely identical. You could write this down just as a cookbook. And obviously, this is, if you do this by hand, this is a lot of work, because every period you have to do the calculations, and very similar calculations, and hence this is very suitable for implementing that numerically. Okay, So in the old days, I guess you had just a bunch of people doing those calculations. You know, one for every control that you pick. Okay. And nowadays you cramp all these individuals into a small computer, and this is more efficient to do that. Okay, so it's once you have the Bellman structure, and once you have the last period, it's just an algorithmic going through the calculations. Okay, and another thing that is important, I think maybe this is also a little bit confusing in a sense. When doing this algorithm, you just focus when finding the optimal control just on the right hand side. So everything you need to do in calculation wise is basically the right hand side. So you go through the right hand side and calculate everything. The left hand side is just for you the definition basically that you put to the for choosing the next period or the period before. Right, so you just do every calculations with the right hand side, and then you get an expression for the right hand side, which you can write down. And the thing is that this expression that you just derived is equal to the value function, and this is what you need in the next recursive step. Okay, so this equation is basically just the lever, I think, the charnier. Between the parts of the algorithm. Okay, maybe this is also helpful when thinking about the numerical implementation. Okay. Do you have questions so far? Okay, then the last step. I mean, what you usually would do, you would do this 2 or 3 rounds, and then you would find some pattern. Okay, and then you would hope that there exists some pattern that remains stable somewhat through time, and then you pick this pattern and move along. And this is what has been done here already. It is said, okay, look, suppose you by just going through the Bellman equation, we know that the pattern is looks something like that. So we know the form of the Bellman equation at some point in time tau. So we do not focus on capital T or capital T minus 1, but we directly focus on some point in time tau, and we know how that looks like. And can we calculate the optimal control? And the approach is again exactly the same. So we focus on the right hand side. We have to say something about how the v tau x tau looks like. We can plug everything in, so we know the functional form. We know the expression for the x tau, so how I affect my state tomorrow, and I know the probability structure. And what you will see is that we have the same as before. So if we write down the expected value of the value function of capital X tau, this is barely readable, I'm sorry for that, then you find just an expression that is just a function of your control. But this is what you needed, right? Because this tells you how your control in tau minus 1 affects the rest of the planning horizon. This is what tells you this equation. And again, you can find the optimal control just as before, right? You take the first order condition. This is the contemporaneous effect. We know that. This is the effect on the expected value of the value function. This is usually the thing that we do not know, right? This is the problem that we need to find. But in this case, we are lucky, right? Because we know the v, we know the probability structure, and then we can derive an explicit expression. And this is the reddish thing here. And we have again a u tau minus 1 of 1/2. And it turns out that the best thing to do is in every period to choose the control as 1/2. Okay. Okay, that was my last slide concerning the pen and paper approach. Do you have questions so far?
Not a question maybe, but I really like the extensive explanation of the different steps, because my solution doesn't even look half of it. Like, it's very extensive and explanatory. And so it would help, I think, to put page numbers on the solution.
Oh yeah, that's true. Oh yeah, that's
sometimes
true.
you jumped to the front.
Yeah, that's true. I'm sorry. That's true. That's true.
Yeah, maybe for the next solution.
Yeah.
I really like the format of this.
Thank you. No, I will put just text numbers to just put page numbers into that. That's easier. That's true. You're right. I'm sorry.
Thank you.
Anything else? So again, maybe just there's a term in what people in the States sometimes use. If you train something, you need to have muscle memory, so that basically if you train to do something, so your muscles kind of have to remember the steps that you make. If you, I don't know, learn to cut an onion fast, or if you learn to, I don't know, ride the bike or something, so you need, muscle memory. I mean, it's no muscle memory, it's a brain memory. And the reason is that you go just very slowly, step by step to learn this muscle memory. And the same thing I've tried here, just to go little step by little step, just to that this ingrains into your brain. Because once you know that, well, then you can go fast. Then afterwards, it's everything is always the same. It's always the same approach, and then you can just scale it up. Okay, so I think, Andreas, it's your turn.
Yep.
Thank you.
Okay, then let's go through the numerical part, or through the numerical exercises. And the first was to take the results that Jörg just derived, so the optimal control is always 1/2, and then simulate 5,000 paths, 5,000 optimal paths. So in each period, you choose a control of 0.5, or you invest or you consume half of your wealth. Do that 5,000 times, and then plot the empirical CDF of all the realized values that you have in the end. So what we are going to do is, first, we initialize our parameters for the simulation and some empty vectors to store the values that we receive and our state variable x over the time periods. So r is equal to 5,000, the iterations of our simulation, and capital T or TT in here because we don't want to overwrite the true value in R is 10. And then we can initialize an empty object for the values that has length R and is a numeric, so it's just numbers. And we can do the same thing for the states with a length of 10, so capital T. And also these are just numbers. And then we set the first of these numbers to 1 because in the first period we start with a wealth or in a state that equals 1. What we then need is 2 loops. The first one goes over all the simulations that we do, so all these 5,000 steps. And the second one is the inner loop that iterates over the optimal path. So we start at 1, we invest half of our money, and either it turns out to be a good investment, then we get 8 times what we invested, or it turns out to be a bad investment, and then all the money is gone. So let's do this in the inner loop. That one goes always from 1 to capital T minus 1, because in the final period, we already know what we do. We don't have any decision to make, but before that, we can invest or not. The future state is then either 0 when the investment goes wrong, or it's 8 times what we invested if the investment was a good decision. So let's just take our investment. So 0.5 times our current state. So the optimal control is always to choose 0.5 of what we currently have. And then with the sample command, we can draw a random number from any given vector. In this case, the vector 0 and 8, because either we end up with nothing or we end up with 8 times what we invested. and of size 1 because we only draw a single time in each period. And then this loop iterates from 1 to 9, and each time computes our new state based on the simulation from our old state. Once we have these states, we can compute the values, just as you can see the formula on the exercise sheet, and by the very same formula that Jörg has been using extensively. So we have this whole sum expression here, so the sum over all periods from 1 to 9, plus what we have left in the 10th period. And when we run all this code, this goes very quickly, and then we can plot the empirical distribution function. And what we see here on the right is that obviously in 50% of the cases, we end up with 0 after the first period. So we have a value of 0.35 something around here in 50% of the cases. And in 50% of all subsequent cases, we also go down to 0 with our state, or the state is 8 times what the state was before. And obviously, all these steps are just half the size of the previous steps. So these are the values, the realized values that we obtain if we run 5,000 times our life of, say, 10 periods and do all these 10 decisions 5,000 times. The next exercise is to ignore everything we know, ignore that the optimal choice is to invest half of our wealth, ignore the explicit value function, but do the whole thing, the whole exercise numerically. So we have here a time horizon, in this case of t equal to 7, so it doesn't take that long. We should not use any information about the functional form of the value function, apart, of course, what we know in the last period. That is, we just have no decision to make here. And we should be careful, and that is, in this case, a very important thing, to define a reasonably large and reasonably fine grid for the state variable. So let's first initialize everything as before. So we have the values and the grid here. We have an initial grid that goes from 0 to 8 to the power of 6, because we have 6 times the decision whether or not to invest. In the best case, we get 8 times what we invested. We can invest everything at the maximum we could invest. So 8 to the power of 6 is what we would receive in the final period if everything goes well. So we need to define a grid from 0 to 8 to the power 6 to cover the whole possible state space. And we start here with an equidistant grid, so the spaces between 2 grid points are the same, no matter whether we are between 0 and 5 or between 1000 and 1005 and so on. So in this case, we have a grid that is equidistant with a distance of 10 between grid points. That gives us a grid size of roughly 20,000 grid points. So a rather large number to compute the value function on. So we need lots of iterations to compute the value function for each of these potential grid states. You'll see later on. Then we can create a list for our value functions, an empty list just with a list command. And because we already know what to do in the final period, then we of course know what the value function of the final period is. So we can compute the value function at capital TT. So in the 7th period, it's just a function, and what it returns is 0.5 to the power of TT times the square root of 2 times x, so 2 times our state. That's the value function in the final period. And remember, this is by definition already a function. So we can use this object v at TT as a function. So just put round brackets behind it, plug in any number, and this will return a number for you, namely the value function at period 7. Now what we need to do is to go back now from period 6 to the first period, go over our grid of potential states that we are in, And for each of those potential states, compute the contemporaneous utility plus the expected value function of the rest of the remaining time. Optimize over this in order to get the value function of the current period. So ignore the print command here, just shows you how long this takes. Then we can set up our expected value as a function as well. And we know that we have a very simple stochastic structure in here. With 50% probability, we end up with nothing in the next period. With 50% probability, we end up with 8 times what we invested in the next period. So what our expected value function returns is just the contemporaneous utility. So 0.5 to the power tt times the square root of 1 minus what we invested times our state, plus with 50% probability, the value function of next 0. So the value function of tomorrow of we don't have any wealth anymore, plus again with 50% probability, the value function of tomorrow with the state of 8 times what we invested. And the expected value function here has 4 arguments. The first one is the one we want to optimize over, so the optimal control, so the control, how much do we invest, what is the share we want to invest of our wealth, the second argument. The third one is the time we're currently in, and the fourth one is the value function of the next period. So we could also call this one vt plus 1 or something. This one here is the value function of the next period. We can then also define a grid, or need to define a grid of value functions. Previously, we only defined a grid of potential states. Now we define an empty grid of values for all of these state grid points here. And then we go over this whole state grid. For each point in the state grid, we optimize the expected value functions with respect to the control. So we find the optimal control for each potential state. And we return the position of the optimal control. So what is, we return not the position of the optimal control, but the value of the value function. So the height, so to say, of the value function. We store this in the value grid. And this grid is then, represents then the value function of period t. Well, this grid obviously is not a function, but just a grid. And we would like to get a function in order to use the value function as a function, technically as a function, as we did with the final period. And we can do this. We did this all the times before with linear interpolation. Right here we do it with spline interpolation to get a smooth function. So just piecewise polynomials between the points of the grid, instead of piecewise linear function between the points of the grid. So these splines then are actually a smooth function and not more, they don't have kinks anymore. And then we are basically done. We can run this whole thing, and I'll just go to copy and paste everything to run all this. And you can see that it started at some time, then it takes a couple of seconds to run this code, to run through all the periods, because our grid is rather large. And what we get after 15 seconds of computation is that we have a value of 1.25 roughly, where the true value is actually 1.5. So we are rather quite far away from the true value. That is very unfortunate, and the reason for that is that the grid is rather is not fine enough here. So the grid always is important when formulating these problems, or when coding these problems and solving these problems numerically. So let's just cut the grid size in half, go for a finer grid, and look what happens. Obviously, all computations take more time, which is a penalty for us now because we have to wait longer. In this very, very simple problem, it's not a big deal because whether it takes 15 seconds or 30 seconds doesn't really matter. If you have more complicated problems, then this, of course, might be a hurdle or a barrier because you don't want to wait hours or weeks or months for your results. So let's have just a brief look what happens. We are now, it took 23 seconds, no, 27 seconds, so roughly twice the time, which makes sense because we doubled the grid size, doubled the elements of grid points, and we are much closer to the true solution of 1.5, so only just a few % off. I would like to spend a couple more minutes on to the grid if you'd like, because you can do the same exercise with a much more cleverly chosen grid in a fraction of time, because if you look at this equidistant grid, that goes from 0 to 8 to the power 6. 8 to the power 6 is 260,000 and something. Then you see that, and if you consider the stochastic nature of our process here, then you will only end up at 8 to the power 6 with a very low probability, with 1/2 to the power of 6. So you end up there in only very rare cases. You'll end up at a value of 8 to the power 5, even also with a very low probability. In fact, 87% of this grid are rather useless and will only be used in 12% of these cases. Additionally, these only 12% of cases that you end up with a high wealth are also weighed down by the discount factor, by the very strong discount factor, so they don't contribute to the value function that much. So most of the grid here is rather useless. What we could do is then define a grid not equidistant between the whole range or on the whole range, but to define the define the grid piecewise equidistant between 8 to the power I minus 1 and 8 to the power I minus 1 for all the possible time periods. So we have a very fine grid for states between 1 and 8. Then the distance between grid points increases for 8 to 64. It increases even further from 64 to, what's 8 to the power 3? I don't know. 512, and so on. So the grid gets wider and wider with each, the higher our wealth is. Because we know that high wealth can only occurs very rarely, and secondly, contributes to the value function in the end, also to a very small fraction. What we then do is we define the grid piecewise. Each piece has a length of only 20, so we end up with a grid of length 122. So instead of 50,000 grid points, we only have 122 grid points, and all the rest is exactly the same as before. So I won't go through that. Just mark the code, run the code. It takes a fraction of a second to run, and we end up with almost the true value of 1.5. So we can speed up many problems significantly by choosing grids in a more clever way than just choosing equidistant grids. All right, that's what I wanted to say on the numerical part. Do you have any questions remaining or comments or anything?
I just want to add just super briefly to can you go back to line 50 or so? No, a little where the optimization is. So just a little bit. Yeah, there it is. So basically, just for you to see that the thing with this first order condition calculating blah blah blah. This is basically in the done from line 60 to 66.
Yeah.
Right. So basically, what you do just for you guys to see that instead of having this first order condition, what the computer does, it just picks one value and calculates the optimum and stores that and goes on, and already plugs also into the value function. All the things that we did by hand and, you know, plug it in, back, and is just done in this 5 or 6 lines of code, or 10 lines of code, where you have then at the end of the day the new value function for the thing. So this is I think a nice way to where those two approaches meet, basically. The difference here is obviously that it's much more efficient to just let the computer do those calculations.
Okay, then I think we can go back to you.
Sorry, I have a question.
Sure.
Could you please go?
I just lost my internet connection for a second. Where should I go?
To the first part of the exercise.
Yeah.
A little bit. Yes, I don't understand why in line 17 you compute the sum, because when we did the pen and paper exercise, we just evaluated the function at the time period we were in. So why do you sum now everything?
We sum everything because we want to compute the value function as of now. So as of I am in period of time 1. That is, we sum over all the utilities over time. So from today, to tomorrow, to the day after tomorrow. And we can do this in this case because we have simulated the whole path. So we have taken the stochastic nature of our problem to simulate it to get a realization of the problem. So we are no longer, down here, we are no longer computing the value function as of today of having a state, but a realization of this value function. Because we no longer, we have, everything has already realized.
Mm-hmm.
This is the same we did in the pen and paper approach.
I thought we didn't have the sum term anymore, or we did? Because we always wrote the value function only for period t-2, and we didn't have the sum, or I got it wrong, sorry.
So what Andreas just calculated is basically this expression, okay, knowing that the u, this is optimally chosen, so this is the value function, is 1/2. So what you basically have is you have all this this sum for every ut is 1/2. So just plug in the 1/2 and calculate that. But obviously you need, so you do not calculate the expected value, but you assume that you have a path of all the x's that you have already calculated. So what Andreas did is he just simulated one path of all the x's. So this is what you know, this is just a vector of numbers. So all the x's are known, and the u is 0.5, you know that as well. What you then do, you just calculate what is in the round brackets. This is just the sum of this thing plus this thing. And what he then does is he picks another x path and plugs this in, and then you get a new value, okay? And he does this 5,000 times.
Okay.
And then he calculates basically or he shows the distribution of that. And he could also calculate the expected value of that, I guess. So this is where the sum hits us, but it's not. I think you were referring to this. I'm sorry, to this, I guess.
Yes.
But this is a different kind of animal. This you write this recursive structure to find the optimum. What Andreas does at the beginning is, knowing you have the optimum, you just calculate what the outcome would be.
I understand now. Thank you.
Yeah, I think that's quite important to understand the difference between using the computer to simulate what could happen if we acted according to the optimal decision rule, which is what happens in exercise part C. So this is what you just asked, and using the computer to find the optimal decision rule, which is a different task. So you can use the computer for different things here, either to find the best choice or the best policy, which is more difficult than using the computer to just simulate what would happen if you already know the optimal decision rule. Okay. Other questions? So then we go over to the infinite horizon case, I guess. That's you again, Jörg.
Yeah. But this is just actually I just want to show you just one slide to make the point, because we hold on. I have two. Okay, so basically, I to make this point, I do not want to go through through everything that we did. I just want to show you basically two slides. So one slide refers to the new problem. Okay, so now we just consider a situation where there's no end to the planning horizon, and so. Speaking in terms of what we've just solved, this obviously results in a problem that we have no anchor period. So it would be nice to have something else how we can do that, but where there's a shadow, basically there's also light. So this also makes the recursive formulation more easily, okay? Because what we can do, and this is what I've tried to show you just at the beginning, you can write this initial problem in a recursive structure, and then you will see that if you just extract the beta out of this sum, that then the problem is basically the same, except for the fact that you now put yourself into the shoes of the guy being in tau plus 1. So with the help of just extracting one of the betas, okay, you can just rewrite this problem in a nicer way, namely that the functional form on the right-hand side, on the left-hand side of the Bellman equation, and the functional form on the right-hand side of the Bellman equation is identical. So this is what I just referred to you when we talked about the 1/2. You couldn't do that in this case, because then it would totally mess up this recursive structure. Here, the nice thing is that the only thing that differs between basically the situation starting from tau plus 1 and starting in tau, except for a different state, is just evaluation. Okay, so it's just a discounting, and this helps a lot, because then we have only one function that we need to find. So there's just one value function, which is in these autonomous problems, obviously the same over every period. In the finite horizon case, this was not true, right? If you go back to the exercise, and there it was stated that the value function is something like 1/2 to the power of 2 times the state. So you get a different value function for every different point in time. Here, this is not the case. Because this is a nice feature, we can just get rid of this time index and just write the value given that you are in state S, irrespectively of at which time you are, is just the maximum of the utility that you get of the contemporaneous objective, plus discounted the expected value as of tomorrow, where the S prime is just the next period. Okay, so you just need to consider the today and the tomorrow, and we again have the situation that we can use this iterative process, this contraction mapping theorem and everything to find the value function. So the approach is very similar to the finite horizon case, but it's a different interpretation, I would say. So again, in the infinite horizon case, you would focus on the right hand side. You start with some v and do all the calculations that we did before. So we need to know the functional form, we need to know the effect on the S prime, and we need to know how to calculate the expected value, and then we go through the iteration. Okay, the only thing is that here this iteration just leads to one value function that we are after, and in the finite horizon case, every iteration led to the value function of the respective period. Okay, so these are two different notions, but the operative approach. So if you would train somebody just doing it, like the computer, for example, it's basically both is completely identical, and so we can use the same methods that we did before to find the value function. Again, this is then just one thing compared to the finite horizon case where you had many of those value functions, and this is the main difference, I would say, in the interpretation. But the approach is very similar, and since we want to highlight not only the similarity between the finite and infinite horizon case, but also between the deterministic and the stochastic case, we have I think one of the exercises takes up the growth model that we discussed in the deterministic case, where we also try to find, or where we not tried, but where we derive the value function by this iterative process in the deterministic case. And what we do here is we look at a slight extension to the same model, and again want to find the value function using this iterative approach. And this is, I think, the next thing that is on the plan for the last, I don't know, it's not half an hour, 20 minutes or so. And I think this is just what was it that Mark, did you want to? Yeah, we want to go through that. Okay.
Yeah. So we decided not to do this exercise in the breakout rooms in small groups, but I'll just guide you through the solution sketch. And well, as Jörg just said, the exercise is very similar to the one we did before in the deterministic case. So here we have a growth model which is exactly the same as before with a very slight extension. So let me just share that. So we have the same objective function. We want to maximize the sum of the discounted utilities, with the only difference that now we have got an expectation operator in front of that. The law of motion is almost the same. The only difference is that we have an additional variable here, which we interpret as the technology level. So K is, as before, the capital stock. C, of course, is consumption. Log of C is the utility of consumption. We have a normalizing constant A. we have a kind of production function which depends on the capital stock, not on labor, because it's very simple. And we have the technology level, which is new here, theta. And the technology level here is important because we assume that technology is random. So there's randomness coming into the game. And we assume that the technology level is an IID draw from a log normal distribution, which means that the logarithm of theta has a normal distribution, and we assume the expectation is 0 and there's some variance sigma squared. Of course, different assumptions about the randomness of the technology level would be possible. So for instance, here we could also assume that we have just 2 levels, high and low, or just a small number. To assume without any difficulty that the technology level is time dependent. So if it's very high today, it's likely to be high again, relatively high tomorrow, and so on. But I think this is a good choice because on the one hand side, it's more complex than just a finite number of values. So here we have a continuous distribution, but on the other hand, it's relatively simple because it's IID, so it's independent over time. All right, so I hope you recognize the general setting. The only difference is we need the expectation here because we have randomness in the law of motion. Okay. Right, so what are the state variables in this case? You remember from the deterministic case, the state variable was the capital stock. And here we have an additional state variable, which is the technology level. So there are 2 state variables, which is also an extension in contrast to what we did before. Up to now, you only considered value functions which depended only on a single state variable. So this is new, and it nicely illustrates why the number of states might become a problem computationally wise. We still have only one control variable, that's consumption. And the Bellman equation is exactly what Jörg just showed on the slide. So the value function for the current values, we drop the time index here because we only distinguish between the values today and the values tomorrow. And these are the values today. So the value function now depends on 2 state variables, capital and technology. And it's the maximum over the control variable C. And the max is taken over the sum of current utility plus discounted expected continuation value. So the discount factor here is just beta. And we have not the value function of tomorrow, but the expected value function of tomorrow's values. So the tilde signifies that these are tomorrow's values. And of course, the capital stock of tomorrow is deterministic. So tomorrow's capital stock is a function of today's capital stock and today's technology level, which is known. So conditional on knowing today's technology level, it's not stochastic anymore. And of course, the choice of consumption, which we decide on, so we know that as well. So tomorrow's capital stock is not stochastic, but it could be. So that wouldn't be a problem to change that. But in this case, it just happens not to be stochastic. But tomorrow's technology level is stochastic. So it has a log normal distribution. And we know the distribution, that's important here. So we know the law of motion, the stochastic law of motion. We know how today's state variables develop into tomorrow's state variables given the control variable, the consumption. Okay. Right, this is a very simple growth model, and it's so simple that it's actually solvable analytically. And the solution is given in the exercise text. If you enjoy doing analytical stuff, then you are invited to verify that. The solution approach is the guess and verify approach. So you guess a functional form of the value function, you insert this functional form into the Bellman equation, and then you can check whether it's actually the correct guess. And my first guess was actually wrong, so it took me a couple of days until I found out why it was wrong, and my guess was just wrong. But if the guess is correct as it is now, then it works. All right. So you can find the analytic solution in the exercise book, but we just pretend not to know the analytical solution, but we want to do it purely numerically. And maybe just as a warning, Andreas already showed that it really is important how to do it numerically in terms of computational time. So if you choose the grid in a very clever way, then the computation time goes down to to a fraction of what you need when you choose the grid just by brute force. And this is true in general. So the numerical implementation is very important, and there are very many details that matter in terms of computation time. But that's not the objective of this course. So we show how to do it numerically, but we are not going to show you how to do it efficiently numerically. Okay, so this is just a warning. The code we are working on is not efficient code, and that would take too much time, and it's really down to the very nitty-gritty parts of the code, and this is not what we are going to do. This is just a warning. Okay. All right. So how can we do it numerically? Well, before I go into the details of the code of the solution sketch, we have to think about at least three important problems. And it's worthwhile really thinking about these problems before you start implementing it into code. So the first one, as usual, is how can we represent the value function? Because we are going to do value function iteration. That's another warning. That's only one solution technique. There are other techniques how to find the optimal control, but we are only focusing on value function iteration. But in any case, we have to decide how to represent the value function. And of course, there are many different approaches to do that. And you could do it in many different ways. And the solution sketch we are going to present is just one possible way to do it. Okay, so we have to think about how to represent the value function. And this becomes slightly more difficult here because the value function depends on two arguments now, not just one argument as before. Then going back to the Bellman equation. So this is how can we represent this part of the Bellman equation. The next question is how can we represent this part of the Bellman equation. So how can we compute the expectation? Expectations are integrals. So this is actually a matter of numerical integration. And I will very, very briefly deal with that topic. And if time is not enough, if I run out of time today, then we can either, if you don't have time on Tuesday, you can just read it in the solution sketch. And if you would like to come on Tuesday, then we can talk about the details on Tuesday. All right, and then going back to the Bellman equation, of course, the final thing is how can we do the maximization? Well, that's probably the easiest part here because this is exactly the same as before. So as in the deterministic case. All right, so let's start with the first problem. How can we represent the value function? As I just said, the value function now has two arguments, not just one. And therefore, it's quite a straightforward generalization to define two grids, not just one grid. So we define a grid over the capital space, capital stock space, and another grid for the technology level. And they need not have the same length, but of course they could. Both of them should be reasonably fine. And then having two grids, then we can compute the value function at each pair. So if we have nk grid points for the capital stock and n theta points for the technology level, then we have nk times n theta pairs. All right. And you can see that if you have a fine grid for k, say 1000 grid points, and also a fine grid on theta, say also 1000 grid points, then you have 1 million pairs. Okay, so the number of points where you have to evaluate the value function goes up exponentially. And if you had a third state variable, again with 1,000 grid points, then you had 1 billion points. Okay, this is why the number of states is crucial for all these dynamic optimization problems. All right, so we compute the value function at all pairs, which means we have three-dimensional representation. But if we do the optimization exercise, then we often have to evaluate the value function between grid points. And then the question is, how can we do a kind of interpolation in the bivariate case? And just try to illustrate that. Let me just share my screen rather than just the that part. So bilinear interpolation would look roughly like this. Oh, it's not getting larger. All right, so suppose you have a grid over the capital space. Well, this is not really fine. It's 10 grid points or so in this dimension, and you have grid points for the technology level in this dimension. Then you have this space of pairs, and for each dot in the parameter space, you can compute the value function. So you compute the dots up here, and then you just interpolate by linear straight lines between these dots up here. Okay, this is the representation of the value function. So you need three ingredients. You need the grid for k, which is a vector. You need the grid for theta in this dimension, which is also a vector. And you need the matrix of height. So for each grid point for k and grid point for theta, you need the height of this value function. Okay, this means that you have three objects that represent the value function: grid, and matrix. And then you can evaluate at points which are between the grid points. So for instance, suppose you want to evaluate the value function at the red point here, which is between the grid points. This happens very often. And then you can find out which part of the value function is that. So if you look from the top, you will find that the red point is in this rectangle here. And then you can just do linear interpolation in both dimensions, and you add up with the red point, which is exactly on the value function here. Okay, so this is bilinear interpolation. And fortunately, this is implemented in R already. So there's an R package. There are actually many R packages that do bilinear interpolation. I found the fields package quite useful, and the command to do bilinear interpolation in that case is interp surface, which is relatively fast and really built exactly for the case we are dealing with here. So equidistant points in both directions, and then you have this bivariate grid and evaluate the value function over the grid points. So this is the way we are going to represent the value function in this exercise. All right, the command needs two arguments, the grid points for the capital stock, for the technology level, and the matrix of value function values. And then it also, the command has a second argument, because that's the red dot in the illustration. That's the dot where we want to evaluate the value function. So these are the two arguments for the bilinear interpolation command. Okay, that's the first question. How do we represent the value function? The second one is, how can we compute the expectation? Well, for given capital stock and technology level, and for given choice of the control variable consumption, the future capital stock is not stochastic. Okay, the only stochastic part is the future technology level. And we know that the log of the future technology level, or this should be theta tilde, the log of the technology level has a normal distribution. And then there's a nice way to compute integrals in a numerical way, which is called the Gauss-Hermite Quadrature. Actually, I don't know how to pronounce that, Quadrature, I guess, method, which is also implemented in R and which allows you to compute functions of normal random variables. Now, to compute the expectation of functions of normal random variables in a very efficient way. So this is the Gauss-Hermite Quadrature. And let me jump again to a different slide. And if there are any questions, please ask right away. We are already running out of time, I realize. Okay. Can you see the tools and techniques slide? Okay. So this is what Gauss-Hermite Quadrature does. Suppose you have a random variable x, which has a normal distribution, any kind of normal distribution, and you are interested in the expectation of a function of this normal random variable. Then any expectation is just an integral running from minus to plus infinity. So in this case, the integral runs over the function and the density function of the normal random variable. And a very efficient way to numerically evaluate such an expectation, such an integral, is to approximate it by a weighted sum, where the points where the sum is evaluated is given by a certain algorithm, and the weights also are given by a certain algorithm. So the points where the function is evaluated and the weights that are attached to these points are derived from what's called the Hermite Polynomials. And we don't go into the details here. Let me just mention that in R, we have a command, which is called Gauss-Hermite, which gives you these points and the attached weights. So for a standard normal distribution, you can choose how many points to get. So for instance, if we choose 4 points, then we get points 2.3, 0.74, minus 0.74, minus 2.33. These are the points where we evaluate the function, if it's a standard normal distribution. Otherwise, we have to shift that. And these are the weights we attach to that. And then we, for instance, if we want to compute the expectation of this object here, the sine of x to the minus 2, if x has a normal distribution, we could use the Gauss-Hermite Quadrature method. Okay, but I just realized we are really running out of time now. So are there any questions concerning what we did today? Otherwise, I suggest we put the solution sketches online. And those of you who cannot come or don't want to come on Tuesday can read that and run the code on your own. And for the rest of you, you're really invited to come again on Tuesday. And then on Tuesday, we have a look at the solution of this exercise. And we can also have a look at other problems you might mention. Okay.